Before we move on to the further, I would like to emphasize a few things about this compare and the branch instruction because branch instructions are quite important in order to jump to any part of the program based on the condition. So these are actually conditional statements. Now, the compare instruction itself is it's actually a subtract operation. But the only difference over there is that uh, the values are not going to change like in the subtract operation. So there's also compare immediate, which we can compare with a constant value. Now, what is important about these conditional branches? Now, conditional branches, they are actually altering the flow of the control. So if condition is true, do that, and so on. And in AVR assembly, there are at least two conditional jumps for each flag of the status register. And in this table, you're only seeing a couple of those, which are quite important. Now, when we talk about branch equal, which is the first one, so it's actually checking if zero flag is set. So it's actually making the subtract operation, and if it is zero, then the flag is set. Now we can say that the operands are equal, and or maybe after the decrement, operand is equal to zero. In this case, we can use branch equal instruction. And branch not equal instruction, it's similar to branch equal, but it's checking when the zero flag is zero. So it's not set like is given over here. So they can be used both branch equal and branch not equal. They can be both used for signed and unsigned numbers. BRSH and BRLO, which is same or higher or if lower. So BRSH is actually making decision based on the carry flag, as I mentioned earlier. So after the compare instructions for unsigned numbers, it means that the left-hand operand of the compare instruction, which is RD, was same or higher than the right-hand operand. So then, based on that, if we have got if you don't have a carry, then it will do a jump. That means it's satisfying the condition. And BRLO is just the opposite of the BRSH, so it has to check if the carry flag is 1. And that means actually the left-hand operand of the CP instruction was lower than the right-hand operand. And these two, BRSH and BRLO, can be used to compare actually unsigned numbers. So in order to compare the signed numbers, we actually need to use BRLT and BRG. Okay, so that's the difference that we need to know about the branch instructions. And BRG and BRLT, they are making the decision based on the sign flag, which after the compare instruction for the signed numbers, it means that the left-hand operand of the compare instructions was greater than or equal to the right-hand operand. And BREG can be branches into forward or backward directions, and BRLT also has got similar properties, but it's checking if sign is equals 1. Okay, so that's all I want to say about the branches. We can carry on with the serialization of the data, which we already seen right rotate and left rotate. We also have So when we talk about serializing data, what do we mean by that is if you are sending a byte of data one bit at a time, for example, from a one pin of the microcontroller, you can actually do that in two ways. Either we are using a serial port, so we have to configure the serial port, and there's a very limited control over there, which we are going to discuss this in further. Another method is we can just send out one data bit at a time from a microcontroller pin. And in most of the new devices, like LCD, analog to digital converters, ROMs, now they are actually connected directly, so we can actually send a byte of data at one bit at a time. Now, how are we doing that? We have got instructions like LSL and RSL. LSL and LSR actually, not RSL, LSR. Now, what do we mean by LSL is logical shift left. Okay, so like we have done with the rotate, logical shift left, we have got a data. Again, we have got the carry, and we are feeding in 0. So in rotate, we were rotating it by feeding back in to the LSB, but in the shift, we are always feeding it with zeros. Okay, so if we look at this example and we want to do a shift, for example, we have got the carry, which at the start we set it to 0, and then we have got hex 26, which is 0010 and 0110. And at this part, we are actually feeding in zeros. So after the first logical shift, 0 comes over here. This 0 fits in over here. So we will have, or let's put it this way, 0, 1, 0, 0, 1, 1, 0, 0. Okay, so we shifted left 1, and we have to do that 2 more times. So this 0 will be shifted over here, and another 0 will be shifted over here. And then this 0 over here, and then third 0, and then 1. And this one is shifted over here, and the 0, and 0, and 1. And then once again, this one will be shifted. Another 0 is coming in, and that will be fit in 0, 0, 0, 0, 1, 1, 0, 0. And this one is on the carry bit. So this is how we can perform the shift operation. And when we are doing logical shift left, we are actually shifting from right to left, and 0 enters from the least significant bit. That's always the carry. Shift left instruction is actually it's multiplying the contents of the register by 2. Okay, so you can check the numbers over here. It's 38 at the start, then it becomes 76, 152 until the carry is 0. When the carry is 1, it's not doing that operation. Okay, so when carry is 0, the logical shift left is actually means that it's multiplying the contents of the register by 2. Another instruction is logical shift right, similar to logical shift left. Now this time we have got it on feeding it from the left MSB to LSB and to the carry. So again, the similar instruction, 0 is fed in, we have got 0, 0, 1, 0, 0, 1, 1, 0, and the carry is here. So what will happen when this one is shifted in? These are all moved to the right, 0, 0, 1, 1, and that 0 comes over here, and then we feed in another 0, that one shifted over here, and then we have got 0, 0, 1, and this one is stored in carry. And the last one, as we are doing 3 logical shift right, and the last one, we are feeding in 0 again from the left. These are all zeros. This is 0, this is 1, this is 0, 0, and that will be 1. Okay, so 38, 19, and when the carry is 1, is 4 and 9. So what does this operation is doing? It actually divides the content of the register by 2, and the carry flag contains the remainder of the division. Okay, so you can use logical shift right in this approach as well. Another instruction that you might be familiar with from logic design course, arithmetic shift right. So arithmetic shift right is another operation which we are doing based on the shift again. But the one thing that is important over here, we are always skipping the most significant bit. Okay, and we are shifting the rest of it. So logical arithmetic shift right, ASR, and the register. It can divide the signed number by 2. And if you have done in logic design, we have done the boot multiplier. Boot multiplier, we're using arithmetic shift right operation at that time. So this is the instruction that we are going to see now. So in arithmetic shift right, as bits are shifted from left to right, MSB is held constant and the LSB exits to the carry flag. So the register, the carry, and MSB is here, LSB is here. The most significant bit is fed back in. So we are actually holding the most significant bit over there, and we are not changing it. Okay, so let's give an example to that as well. Where we have got D0. So D0 is 1, 1, 0, 1, 0, 0, 0. So when we kept the MSB over here, then this is 1, and also it's going to be shifted. So it will be over here as well, and this will be here, and this will be here, and then 1. This has to be 4 bits, and 0, 0, 0, and this one goes to the carry. Then another arithmetic shift right. We keep 1 over here. We have the 1 over there. This one will be here. This one will be here. This 0 moves to the lower byte, lower 4 bits, and then 1, and then 0, and then 0 again, and this one goes to the carry. And it repeats 1, 1, 1, and 1. This is 1, this is 0, 1, and 0, and this is the carry. Another one, this is actually repeating a couple of times. So 1, 1, 1, 1. This one moves over here, this one moves over here. This is 0, and this is 1, and the carry moves to the last bit, this significant bit moves to the carry. And once again, last one that we want to have it. So 1 is staying, 1 is shifting, 1 and 1 again. And this one moves over here, 1, 1, and 0. And this one is in the carry. Okay, so minus 48, 24, 12, 6, 3, 1. As you can see, it's actually dividing. We are generally using arithmetic shift right with these signed numbers. Okay, so if you have any questions related to these, please note those down, and you can ask me during the live lectures. One more instruction which is not mentioned in the lecture notes at the moment, just want to mention that at one as well, is swap instruction. So what is swap instruction? It swap the nibbles. Okay, so for example, we have got in a nibble d7 to d4, and then d3 to d0. So after the swap, this becomes d3 to d0 and d7 to d4. Okay, so let's give an example to that. We have got 0, 1, 1, 1 and 0, 0, 1, 0. So if we apply the swap to that register, this is going to be 0, 0, 1, 0 and 0, 1, 1, 1. Okay, so we can swap the bits based on our needs. Okay. Another interesting thing or important thing in AVR assembly is the BCDs. So you have seen BCDs in logic design, but we also have BCD representations in microcontrollers as well. So if you do remember BCDs, we have got binary coded decimals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we are actually using 4 bits to represent these. Okay, so we have got 1, 0, 0, 0 and 1, 0, 0, 1. Now, In AVR, we can have two types of, or not say not AVR, but in general, in the computer literature, uh, we can have two types of BCDs that we use, unpacked BCD and the packed BCD. You might ask, what's the difference of packed and unpacked BCD? Now, the unpacked BCD, the lower four bits of the number represents the BCD number, and the rest of the bits are zero. So let's say I want to represent 8 as a unpacked BCD. Now 8 is 1000. Okay, so we can have 100 in the lower 4 bits, and the upper 4 bits are zeros. This is unpacked. Or maybe we can try 3. Now the BCD of 3 is 0011, and in front of that, 4 higher bits are going to be 000. These are unpacked. Now, with the packed BCD, we actually have, in a single byte, we have got two BCDs. So, for example, 8 and 9. So, 1000 and 1001. This is packed. Okay? So, as this is packed, we can actually unpack this. Okay, and in one byte we can store two separate BCDs, and whenever we want we can unpack this and we can have 000, 1000, and this one as 000, 1001. Okay, so this is a kind of operation that we perform when we are using BCD to ASCII conversions and so on, and these can be used. So ASCII and BCD code for digits. Now ASCII is actually using a 3, number 3 in front of the decimal numbers. Okay, so 30 is 0, 31 is 1, 32 is 2, and so on. And these are all represented in hex. So the binary equivalent of that is 01100, because the binary of 3 is 011, and then we have got just the BCD numbers. Now, if you want to use unpacked BCDs, then you just have zeros in front of it, and then you have got the BCD numbers. Now, there are a couple of things over here. To convert from BCD to ASCII, first we have to unpack it like that, and then we can do a, let's say, ORing or masking, or bitwise AND or bitwise OR, and we can set the first bits as 3, and we can have 38 and 39 as a ASCII representation. So over here, pack BCD is 9 and 2, then we unpack is 09 and 02, and then when we over them together, we set it as 1, 1, so it's going to be 0011, which is 3, 9, and 3, 2. And that will actually do the packed and unpacked operation. Okay, so maybe we can do a simple example. In this example, we can have, we have to load packed BCD into R20 and convert R22 to ASCII numbers. And place them in R21 and R22. Okay, so what do we need to do? We are going to write a program and load pack BCD into R20. We can use any numbers over here. Let's say LDI R20 0 hex 45. Okay, so now the pack BCD is 45, let's say, and this is loaded into R20. Then what we need to do is we need to have a copy of this, because as we are going to separate it, there's an instruction called move, which actually copies the content of the register. So I'll say in R21, just copy the contents of R20. Okay, so both R20 and R21 now has got hex 45 in them. And what I can do is I can use bitwise AND operation and I can use R21 and I can say 0 hex 0F. I'll show you the register operation as well over there. So now, as I have got in R20 hex 45, when you AND them, the 4 part is going to be ended with 0, so it's going to be 0, but 5 will be ended with F, so it will remain the same. Okay, so in the end, over here, R21 is equals 0, 5. Okay, then if we carry on, after the AND I can do OR I, and I can set the ASCII bits for R21. So in order to set that ASCII bits, I just need 3, so 0 hex 30. Okay, so this means that this is actually going to do is 0011 is going to be masked with ORed with 000, and I will end up with 0011. And the 5 is going to be ORed with 0, so it will end up with 0101. So now I have got 3 and 5, which is an ASCII 5. So then I have to repeat the same thing for the 5 for 4 as well. And in order to do that, as I already got it in R20, what I can do is I can say swap R20. Now this is actually going to swap the lower 4 bits and upper 4 bits. So this will be like 0 hex 5 for now. Okay, and then I can AND I again, like I have done it over here, R20 with 0 hex 0F. Let's do this in the same color. AND I R20 0 hex 0F. Now this means that my 5 will be 0101 will be ended with 0000, and 4, which is 0100, will be ended with 1111. And this will end up with 000 and then 0100. So now I have got 4 as an unpacked BCD. And again, I just need to OR that R20 with hex 30, so I can add this ASCII bits in front of it. So this is actually going to be 0011, 0100 when I OR them together. Okay, and that's all you need to do. You can use any registers, you can use any numbers, and you can try this, and you can see how it is going to be performed. You can also do write a ASCII characters 4 and 7 to R21 and R22 and convert them to a packed BCD. Now, if you initialize these as 4 and 7, okay, this is going to be an ASCII character, okay, or you can assume that it is an ASCII character. It's a text character. Its hex is 3, 4, and 3, 7. Okay, now I just want to get rid of these 3's first, but I also need to copy this, or maybe maybe we can do a swap and then copy. So mask the upper bits, okay, and for R21, now this one becomes 0, and this will end up, maybe I can write that over here. So NDI is actually going to do, we have got 0011, 0100, and when we mask it with 0f, this is the AND operation. So this is going to be 001, 0, and these are 000. Now we have got the 4 over there, and we have got 0 over there. And if we do swap, this is going to be 4 and 0. And then I just need to do the same thing for the other bit, which is 7. And this is going to be 0011, 0100, sorry, 0111. And again, masking it. So 0111, and these are going to be zeros. So now I have got 0 and 7. And in this case, I have got 0 and 7, and I have got 0 and 4, or 4 and 0, sorry. That's after we swapped it. So these are the two values that I have got, which are unpacked. Now I just need to combine them. So I can just use OR function, okay? So for 0 is going to be 0100, 000, and then 0000 and 0111, okay? So this is 4 and 0, this is 0 and 7. And when you OR them together, this is going to be 1110, 0010. So now I have got 4 and 7 on the same register. And if you want, you can copy this result with a move operation to another place.